In this video you will learn what Kirchhoff's second rule actually means, the famous loop rule, and how it can be used to calculate how voltages are distributed in a network where resistors are connected to each other in series. And you will also learn here how to set up a loop equation, how to solve it, and how reference arrows can be used in a circuit. And by the end of this video we will look at the significance of the loop rule and Kirchhoff's laws in everyday electronics. My name is Andreas from The Fearless Engineer, and here we go. Now let's start with a broad definition of the term loop rule. For example, on Wikipedia you will find that the directed sum of the potential differences, that means the voltages, around any closed loop is zero. So here we have this expression, this term loop, and it refers to a certain path in a circuit. A path which you follow along the connecting lines and across components in a circuit. And this path needs to be closed in order for this expression to hold. So we are following a closed path through a circuit, and if we sum up the voltages in this closed path, then the sum is going to be zero. That's basically, in a nutshell, the meaning of the loop rule. Before we look deeper, let's quickly recap some issues which we have discussed in previous videos, especially the first one, which states that the term voltage describes the loss of potential energy in the electric field between two potential points. So in order to properly understand what voltage and what potential difference means in this definition up here, you have to understand that the potential, the electric potential in a circuit is generated by the electric field in relation to the position of the point inside this field. For example, across or above a certain component, let's say a resistor, and below, and across this resistor, when the electrons flow across this resistor, the electrons lose electric potential, so there's going to be an electric potential difference between the top and bottom point of this hypothetical resistor, and this is what we refer to as voltage, so a difference in electric potential between 2 points. The second is, on the way from one terminal of the battery to the other, the potential energy of a charge is converted into kinetic energy. So we have a conversion going on. Energy is never lost, it's only converted, and the conversion happens when the electrons flow from one terminal to the other, and they leave the potential energy behind, so to speak, in this analogy, and the potential energy, when it's getting lowered while they traverse a certain electrical component, this potential energy is then converted into a movement, and this means kinetic energy. And the loop theorem, the loop rule, answers the question of how an applied voltage generated by, for example, a battery is distributed over several components. And basically this answers the question how much energy is converted from potential into, let's say, heat or kinetic energy when certain elements in a circuit are crossed, for example, a series of resistors. And the loop theorem helps us describe this amount of energy loss and the distribution of losses across all the components within this closed path through a circuit. Let's quickly review the junction rule, which we have discussed in previous videos. In a previous video when we talked about Kirchhoff's first rule, and the junction rule is about the distribution of currents in a network. And it states, this first rule of Kirchhoff states that in each branch of a circuit, the sum of the currents flowing in is equal to the sum of the currents flowing out. And you can formulate this in a mathematical manner by saying that the sum of incoming or inflowing currents and the sum of outgoing currents is zero in total. And Kirchhoff's first rule describes the conservation of charges in electric circuits and states that charges are never lost. Charges have to go somewhere, they cannot simply disappear. So every charge that enters a certain node, a junction in a circuit, must go somewhere else in another direction within this circuit. That's Kirchhoff's first rule. Now let's take a look at the loop rule again. I have prepared a small simulation for you, and in this simulation we can see a voltage source on the left of 5 volts. We can see several resistors, 10 ohm, 20 ohm, 30 ohm, and the color code here means that the electric potential is highest at the positive terminal of the battery. It's at a full 5 volts. And while we cross each component, first resistor, second resistor, third resistor, you can see that the color gradient changes from bright green to darker green and then finally to gray. And gray means a potential energy or electric potential of 0. And you can see that in the simulation that in each branch the sum of the partial voltages is identical to the voltage of the source. So this is a branch. Of course, we don't have a second branch, but in a second branch it would be exactly the same. When we start traversing from the positive terminal to the negative terminal across these components, you can see that the electric potential drops while we traverse the first resistor from 5 volts to 4.17 volts. And this drop in potential is equivalent to a voltage drop of 0.83 volts. On the second resistor, we have a voltage drop of 1.67 volts. And finally, on the last one, we have 2.5 volts. And if you compute the sum of these voltage drops, then you arrive at an overall voltage drop of 5 volts. So on the way from one terminal to the other, the entire potential energy of a charge is converted into other forms of energy. And this might be kinetic energy, but can also be heat, which is generated when traversing a resistor here. So the entire potential energy is converted into other forms. And now we have this second branch, which I've just been talking about. We still have the first branch, which we looked at in the previous slide. Now we have a second branch, and please note that both branches share both the input and the output junction. And if you compute the sum of voltages again, we have done this for the left branch already. Now we can do this for the right branch as well. And if you look at 5 volts minus 3.33 volts and 3.33 volts minus 0 volts, you get the voltage drops across these two resistors here, R5 and R4 and R5. And the sum of both resistors is identical to 5 volts, so the same as the source. So the voltage drop, and this is an interesting point here, the voltage drop is independent of the resistors in the respective branches. This means I could replace this first resistor here, R4, by a 10 ohm resistor, and still the overall voltage drop in this branch here would still be 5 volts. The distribution of voltages across these two resistors would change, obviously, but nonetheless, the overall voltage drop over this branch would not change with me changing this resistor value. So the potential of the junction alone, of both junctions, determines the voltage drop. And in the case of an ideal voltage source, this is also independent of the components in the circuit. We will look at non-ideal, at real voltage sources in a very short time. But for now, what we can see here is a perfect voltage source which always provides 5 volts. And for such a source, the voltage drop is identical to 5 volts in both cases for both branches. Now let's take a look at this very colorful version of the same circuit. Kirchhoff's loop rule states that the sum of the voltages in a closed circuit, in a closed loop, is always 0. And here you can see 3 closed circuits, 3 loops, which can be identified in this small network here. You always start at a certain position. Let's take the blue loop, the blue circuit first, and we start directly above the voltage source, but do not yet incorporate them, this source. So we start. This is an ideal connector line which does not have any resistance at all. Then we come to the first resistor, R1. And across R1 we can measure a voltage drop which we call U1. And this is what you find here. And we count it positive in this equation here because we move in the direction of this reference counting arrow. So the counting arrow points from the higher to the lower potential and thus determines the sign of the voltage. So if we move into reference counting arrow direction, we count it positive. Then we get the second resistor, which provides us with U2, then U3, the third resistor on the bottom here, and then we arrive at the power source again and we move against the current, the reference arrow direction. And this is why we need to consider the source voltage U with a negative sign sign here. And the sum is 0 in this case. We could have also traversed this rule in the other direction, and if we had done so, all the resistor voltage drops would have had a negative sign and the source would have a positive sign. So the overall equation would not have changed, because we can simply multiply it by -1 on both sides and still do not change the meaning of this equation here. But if you choose to move in a certain direction, you have to consider the directions of the counting arrows. You can do the same for another loop. This is the orange one. We again start across the voltage source. Now we move across the voltage source in the reference arrow direction of the source, which is why we consider it with a positive sign here. Then we move against the direction into which the counting arrow across R5 is pointing. This is why we consider U5 with a negative sign, the same with U4. And then we arrive at the source point, at the starting point again, which is why we then equal the entire equation, set the entire equation to 0. We can do the same thing with the rightmost loop. We start with U2, minus U1, because we move against the reference counting arrow direction. Then we traverse R4 in arrow direction. This is why we have a plus and a plus here with U4 and U5, and then we move against R3, which is why U3 is considered with a negative sign here. So in total, it equals 0, just as the others. Now in a formal notation, the loop rule has the following form here. The sum over all partial voltages, UK, in a closed loop, which ranges from 1 to n. If you have, let's say, 4 resistors and a voltage source, n would be 5. And the voltage drops across all these components in this closed loop equals 0. The sum of the partial voltages U in a mesh is 0. But the problem is, or the question still is, why is that the case? We can see this rule, we can understand its meaning from a mathematical viewpoint, but why is it like this? Let's take a look at the explanation. This is basically the statement of Kirchhoff's loop rule. The sum of all voltage drops across passive components such as resistors, resistor 1, resistor 2, resistor 3, is identical to the voltage drop across generated the potential difference generated by a power source. And if you multiply both sides with a charge Q, you get this expression here. And if you recall the video on energy, which we have recorded some time ago, then you know that this product of charge and potential difference of voltage is identical to the potential energy of this charge, which is generated by the voltage drop, which it is exposed to. This can best be understood by thinking of the example with the apple hanging from a tree. The charge Q would be equivalent to the weight of the apple, and the voltage drop is incorporating in this analogy the height above ground multiplied with the gravitational pull of the Earth. And in terms of the circuit we are looking at now, the gravitational pull would be the electric field, obviously, and the height above ground would be the distance, let's say, from one of the terminals of the power source. So we can simply compute this product here, and we can replace these products Q times U1 with the energy of with the energy charges lose when they traverse resistor number 1, the same for 2, the same for 3, and this is equivalent to the total energy provided by the source. So this is the conservation of energy, and we can look at the top again. This follows from Kirchhoff's loop rule. So Kirchhoff's loop rule is basically the conservation of energy without taking account of the amount of charge being transported through a circuit. And now comes the big question: what's the practical significance of Kirchhoff's loop rule? Well, his second rule, the loop rule, it can be used to calculate missing voltages in a network. Also, from the loop rule follows the formula for the series connection of linear resistors in a network. And also, the loop rule can be used to calculate how voltages are distributed across resistors which are connected in series. And in the next module, in the next video, we're going to look at two aspects surrounding the loop rule. The first is we will look at what happens when we connect two resistors or multiple resistors in series to each other. The second aspect is we're going to derive and also look at applications of the voltage divider rule. So the rule behind the distribution of voltages across the components in a loop. And that's all for now for this video. I hope you enjoyed it. If you have any questions, leave me a comment down below. And as always, I wish you a nice day. See you next time here on The Fearless Engineer.